Hey everybody, this is Dr. Jacobs. Welcome to this week's lecture on probability and sampling. So this week, by the end of this unit, there are some things that I'd like you to be able to do for our unit learning objectives. First, I'd like you to be able to calculate the probability of an event. I'd like you to be able to solve problems using the addition theorem of probability. I'd like you to be able to solve problems using the multiplication theorem of probability. I'd like you to be able to determine when to use the addition or the multiplication theorem of probability based on the example. I want you to be able to explain how probability relates to sampling methods. I'd like you to be able to explain the three sources of error that we discussed in this unit. I'd also like you to be able to explain how probability relates to inferential statistics. Let's get started. So probability is a proportion or percentage that tells us the chances that a particular event will occur. This is a simplified definition of what this means, and we will get into what it means a little bit later in this lecture. But for now, probability is a proportion or a percentage that tells us the chances that a particular event will occur. Okay, so introduction to probability. There's going to be some terms that we need to know as we move through this unit. One of those is an event. And an event is a specific observable outcome. So if you watch the Super Bowl, at the beginning of the Super Bowl, they flip a coin, right? So, and if someone calls a heads, the event that we're trying to find the probability for is that is flipping a heads. Okay, so generating event then is slightly different than event, which is a specific observable outcome. A generating event is any process that could theoretically be repeated an infinite number of times, which only has one outcome each time. So when we say theoretical, what's that mean? Don't write that in the comments. You can think about it in your head. Dora the Explorer yourself. If something is theoretical, what does that mean? It means that you're not actually doing it in reality, right? So theoretically, if we're saying there's an event that could happen unlimited number of times, theoretically, we know it's theoretical because we're not able to live forever. We can't keep flipping that coin forever and ever and ever because we are not immortal. And so with a generating event, it's theoretically that could be replicated over and over and over and over again an infinite amount of times, but we really can't do that in all actuality. So then possible outcomes, this is every potential result that could happen because of the generating event. So if we're saying flipping a coin is our generating event, the possible outcomes would be heads and tails, right? So we have two possible outcomes for that. Independent event, this terminology means when the outcome of one trial of a generating event does not impact the outcome of another trial of the same generating event. So if we're back to that coin flipping example, if we flip our coin and it lands on a heads, that actually doesn't influence what our result will be the next time we flip the coin. And that's because you still have either heads and tails the second time that you flip the coin. So mutually exclusive, this means that events cannot happen at the same time. So if we're using the flipping coin example again, if we flip a coin, it's not going to land on heads and tails at any time. It will happen one or the other, right? Either it will happen that we have a heads or we have a tails. All right, so probability of an event. When we're doing probabilities, we're looking at the overall probability of the event occurring if we could carry out the generating event the same way an infinite number of times. So here what we're saying is that if we are looking at the probability event, it would be if we could keep flipping that coin over and over for infinity, we could see what the chances are that there would be a heads or tails. Okay, so there's a formula that goes along with this. Probability of event equals whatever event you're examining divided by the possible outcomes. So for example, if you're interested in flipping that coin like we were talking about, and we want to know what the probability is of flipping a heads, we have the event heads. There's only one of those options on one coin. Divided by possible outcomes, we know there's two, heads or tails. And so when we do that, we can get either the proportion, which is the decimal form, or we can convert that proportion into a percentage like we've been doing across the semester so far. Okay, so we just kind of went through and did this. So let's go ahead and talk through this example a little bit more. If we want to know the probability of winning the coin toss during the Super Bowl, we need to know the number of chances for the outcome we want. So the coin toss resulting in a heads, and the number of possible outcomes the coin can either land on heads or tails in one trial of the generating event. So we know that the generating event is the thing that we could do theoretically an infinite number of times, right? In this case, flipping our coin. And we find that when we plug into our formula, we have PR. So if you see there, capital P, lowercase r, all italicized, and open parentheses and close parentheses, that means probability of an event. So go ahead and put that on to your handy dandy symbol sheet right now. So PR with open and close parentheses is probability of an event. That's our symbol for that. And then you'll notice within there, we put which event that we are interested in finding the probability of there in the parentheses. So we have probability of flipping a heads equals one event, which is heads, divided by two possible outcomes, which is either heads or tails. We see so 1 divided by 2 is 0.50. That is in proportion form. So proportion-wise, we have a probability of 0.50. If we want to convert that proportion into a percentage, what would we do? If you said we would multiply it by 100 and add a percentage sign, you're absolutely correct. So we see that we have a 50% chance of flipping a heads. Okay, so we've been going through this a few times, and we're going to keep practicing it because it's not the only time that we're going to see percentages in proportion form. We're usually more likely to remember percentages because that's usually what we work with a lot more. But in stats, we will often see these things in proportion form. Okay, so often probability is written in the form of a proportion. Each proportion can be converted into a percentage. A proportion falls from 0 to 1. So for example, 0.50 would be a proportion. So if we're going to correspond those to percentages, we know that a proportion of 0 is equal to a 0%. And we know that a 1 proportion is equal to 100%. Okay. So 0 then in proportion form means that the event is impossible. So if we have a die that we roll, so that has a 1, 2, 3, 4, 5, and 6 on each side of the die. If we said, what's the chance that we'll roll a 7 on a die? We know that's not possible, right? So we know that there are 0 chances that it's going to roll onto a 7. And we know there's 6 possible outcomes from one roll of the die. And so that would mean that the event is impossible because it would be 0. 1 means the event is inevitable. So if we go back to the coin flipping example, if we wanted to know what is the chance that we're going to flip a heads or tails in one flip of the coin, we know that it's inevitable. That's going to happen. Either you're going to flip our heads or a tail. So our proportion for that would be 1, or there's a 100% chance that that event is going to occur. So most probabilities that we calculate will fall somewhere in between these. Okay, so again, to turn the proportion into a percentage, you multiply the proportion by 100 and you add a percentage sign to it. All right, so now walk it out. So when we found the probability of flipping a heads during the Super Bowl coin toss equaled 0.50 in proportion form, how do we convert that proportion of 0.50 into a percentage? We see that we would multiply that proportion by 100 and add a percentage sign, which gives us 50%. So there are 2 theorems of probability that I'm going to teach you in this class. The first one's going to be the addition theorem of probability, and then the second one's going to be called the multiplication theorem of probability. So we're going to learn both of these and when you would use both of them. So the addition theorem of probability is what we're going to learn first. It has a nickname. Its nickname is the OR rule. And we use this to calculate the probability of getting one event or another during one trial of the generating event. To use this theorem, both events must be mutually exclusive. What does that mean again? That means that the events cannot happen at the same time. So we can continue. So we have a formula for our addition theorem of probability. So our addition theorem of probability equals the first event divided by all possible outcomes plus the second event divided by all possible outcomes. So go ahead and write this down. You can pause me if you want to. All right, so for this, we need to review a little bit on how to add fractions. So if fractions have the same denominator, we just add the numerators together and keep the denominators the same. For example, if we had 1/5 plus 3/5, it would equal 1 plus 3 in the numerator divided by 5. And so when we simplify that even further, we get 4/5. All right, so let's practice. What is the probability of rolling a 1, 2, or 4 when rolling one die? Okay, so go back in your notes, find the formula, and then try to figure this out before we move forward with it so that you have the practice you need to understand what we're doing. Okay, so what is the probability of rolling a 1, a 2, or a 4 when rolling one die? So again, we're going to use the addition theorem of probability. You'll notice in the question, we say 1, 2, or 4, remembering that the addition theorem of probability's nickname is the OR rule. So that's a little mnemonic to be able to help you understand when to use it. Okay, so here is our formula again. We have the addition theorem of probability equals the first event that we're interested in, find the probability, divide all possible outcomes, plus the second event divided by all possible outcomes. Here we have 3 different ones of those, so we'd have plus the third event divided by all possible outcomes. So when we write this all out, we see that we have PR, open parentheses, 1, 2, or 4. So we don't care if we're rolling 1, 2, or 4. We're trying to find the probability of getting one of those in one roll of the die. So we have equals the probability of rolling, or the possible times that we could roll a 1 on one roll of the die. We know that's only 1, divided by 6, right? We could roll a 1, 2, 3, 4, 5, or 6, plus the second event, which is rolling a 2 on a die. We know that there's only 1 2 on a die, so we only have one opportunity to roll a 2, divided by all possible outcomes, which is 6, plus rolling a 4, which we know there's only 1 4 on the die, so we have 1 out of 6 for that. And so we have 1/6 plus 1/6 plus 1/6. So how do we add those fractions together again? Yes, because they have the same denominator. All we have to do is add the numerators. All right. So when we do that, we see we have 3/6. If we simplify that, that's 1/2. And if we turn that into the proportion, that is 0.50. Okay, so we also have the multiplication theorem of probability. The nickname for this one is the AND rule. You will want to know the nicknames for these. They really will help you. I could quiz you on them too. So just make sure that you do have these. So use this to calculate the probability of getting one event and another event in an exact order. So this is when order does matter. So for the AND rule, the order matters. To use this theorem, both events must be independent events. This means they cannot influence what is going on with the other one. Okay, so again, this means the outcome of one event cannot impact the outcome of the rest of the events. Okay, so we have a formula for this one too. I bet you could guess what it would be based off of what we've done so far. So our multiplication theorem probability equals the first event that you're interested in divided by all possible outcomes multiplied by the second event divided by all possible outcomes. So go ahead and write this down in your notes. Pause me if you need to. So it's good for us to review multiplying fractions. And I actually think this is a lot easier than adding fractions sometimes. Because when we multiply fractions, all we have to do is multiply the numerators together across and then the denominators together across. And so that makes it a lot easier, because with adding fractions, when we do that, we have to have the same denominator. So if we don't, then we have to figure that out. So for example, 2/3 times 2/7, we multiply our numerators together, so 2 times 2. And then we multiply our denominators together, which is 3 times 7, and we get 4/21. Right? So let's practice. The animations are kind of wonky on this, so try not to look at the answer while we go through this. But what is the probability of rolling a 1 on the die, a 2, and then a 4 when rolling one die 3 times? So try to do this without looking in your notebook. So we know first we're going to write PR, and we have a 1, 2, then a 4, right? So we know that we have a 1 out of 6 chance that we're going to roll a 1. We know that we have a 1 out of 6 chance that we're going to roll a 2. And then we see that we have a 1 out of 6 chance of rolling a 4 on each of these. If we want to roll these in the particular order, a 1, 2, then a 4, on 3 consecutive trials of the generating event, we see that we will multiply all of our numerators across. So 1 times 1 times 1 equals 1. And then we will multiply our denominators across. So we have 6 times 6 is 36, times 6 is 216. So we see that the probability of rolling a 1 on one roll of the die, then rolling a 2 on the next roll of the die, and then rolling a 4 on the third roll of the die, that we have a 1 out of 216 chance that we'll do that. If we turn that into a proportion, we see that's approximately a 0.005 chance of this happening, which is in proportion form. If we want to put that into percentage form, we see that we have a 0.50% chance of this happening. So which theorem? Let's practice this a little bit. Now that we know more about both the addition and multiplication theorems of probability, let's take that understanding a little bit further. Say we wanted to know what the odds were of flipping a coin twice and getting 1 heads and 1 tails, resulting in any order. Which theorem would we use? So if we don't care about the order, we just want to know what the odds of flipping a coin twice and getting 1 heads and 1 tails in any order, which theorem would we use? Okay, so if we're looking at this chart, I have a nickel there. It doesn't look like a nickel, unfortunately, because the coloring didn't turn out the way that I wanted it to. But when we see here, when flipping a coin, let's look at this little chart. You'll see I have every possible combination here. We have, if we're flipping a coin twice, we have heads could happen, heads tails could happen, tails could happen, or tails heads could happen, right? So when we're looking at this, what would be the probability of getting a heads and tails in any order? So either heads, tails, or tails, heads. So when we look at this, we have 1 chance that we could get a heads, tails, and 1 chance that we could get a tails, heads, when flipping a coin twice. And so we would actually use the addition theorem of probability for that, right? So we know that we have a 1 out of 4 chance of getting a heads, tails chance. We have a 1 opportunity to get tails or heads. If we add 1 divided by 4 plus 1 divided by 4, we get that 2 out of 4 chance that we're going to flip heads or tails in any order. We turn that into proportion, that's 0.50. And if we turn that into a percentage, that's a 50% chance. So if we go back and look at this little chart, we see that that makes sense, right? Because 2 out of the 4 possible combinations that we have result in either a heads and tails or tails and heads. So then what is the probability of flipping a heads and a tails in that specific order? So flipping a heads first, then a tails. So we look in our chart, there's only how many opportunities to do that just by looking at the picture. If you said there's only 1 opportunity to flip a heads then a tails, then you're absolutely correct. Okay. So when we have no particular order, again, we see that there was a Sorry, I'm trying to move my picture so it's not blocking your view. I don't know if it actually does that in the video, but I'm trying to make it so you can see everything. So we see in the table there is a 1/4 chance of getting a heads and tails result and a 1/4 chance of getting a tails and a heads result. So if we did not care about what order of flipping heads and tails, we would use the addition theorem of probability, which we already walked through. Okay. So here's the math. If I'm going to put the math out for you so you can see the formulas and what that would look like. We see there we have the probability of our event. So PR, open parentheses, says that that's the probability of this event. And then the events that we're interested in is either a heads tails flip or a tails heads flip. Okay. We see that there is one possible chance of flipping heads then tails with 4 possible outcomes: heads, 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 tails, 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 or tails, heads, plus one event, which is tails, heads, divided by 4 outcomes, which are the same as the other. Okay, so when the order matters, though, we see in this table there's only one instance of getting a heads on the first flip and a tails on the second flip. Whenever we want to predict that certain events will occur in a particular order, we use the multiplication theorem of probability as long as the events are independent. So like I said, if you flip a coin and it's heads or tails, when you flip the second coin, you still have a chance to flip a heads or a tails. So they don't bother each other. So if we put this math out and we work it out with using our formula, we see the probability of getting a heads tails. We have one event flipping heads divided by 2 outcomes, heads tails, multiplied by one event flipping a tails, and we have 2 outcomes there, heads tails. All right, so sampling. We discussed 3 major sampling methods during our first unit. What were those? Try to say it out loud. This is good practice, remembering that all of our tests in here are cumulative. What are our 3 major sampling methods that we've used in this class? So we had random sampling, convenience sampling, and snowball sampling. Okay. And so these are important to remember because when we go take our sample from whatever population we're interested in, there's always a chance that our sample actually does not represent our overall population. Okay, so we're going to think of this as why we will come up with different probability values later. We actually won't calculate them. We'll use something else. But in statistics, we'll have a value called a p-value, or the probability of making something called a type 1 error. And those probability values have to be underneath a certain threshold for us to say that we have significant results. That's me getting a little ahead of myself as we move forward. But we'll know that we actually won't be calculating those probability values. We're actually using this unit to understand that there are a lot more complicated ways to calculate probability. But we have kind of a basic understanding what it means so that when we're doing something later, we understand what it means when we have a probability value. Okay. We also have sources of error. We have some in every score. If you remember, we have our obtained score, or the score that you get on whatever measure you have. And within that score, we have what our hypothetical true score would be, or theoretical true score plus error in that score as well. So we have sampling error. This is the difference between what we find with our sample and what occurs in our population overall. So just by taking a sample, we're introducing a chance that our results will not represent our overall population. Okay. And when we get into inferential statistics, that's what we're doing, right? We're taking a sample to try to make guesses about what's going on in the overall population. We also have measurement error, which is the difference between the measurement of our data set and the true value of that data set. And that really bothers students. Students are like, well, will we ever know what the true score is? How do we get that true score? And the thing is, we actually don't. We don't get that true score. We can try to guess. We can try to have the best measures possible, but there is always going to be error in every score that we get just because we measured it. And then we also have random error. This is unpredictable error that occurs during the study and is more difficult to control. People are like, well, how do we know what percentage is random error? We don't. It's unpredictable. And because we have taken a sample, because we have these sources of error, we need statistics. That 100% is the whole reason why we even do statistics, because we know that anything that we measure is not perfect. Anytime we take a sample, it's not perfect. And even if we had perfect samples and perfect measurement, there's random error that happens in anything that we do. Okay. So again, oh, actually not again, this is going to be the first time I introduce this, but when we run the hypothesis testing steps, which we'll learn in the next unit, we're going to calculate something called the test statistic. This test statistic will have some sort of probability value that is connected to it, okay? Luckily, we don't have to calculate that probability value by hand. It actually takes calculus to be able to do, and we're not going to do that in here. Okay, so then we are going to use this probability value to make a decision regarding our research question that we're trying to answer with our data set. Okay, so I know this is a lot. Take as much time as you need to get through this lecture, but know that this probability unit is just to give you a vague understanding of what probability is, because it underlies everything that we do with statistics. We won't be calculating a lot of probability values in here, because we'll do a different method that is easier to be able to do some of these things by hand. I'll be giving you tables and things, but know that probability, although it's very important for statistics and underlies everything we do, this is going to be the extent of what we're doing or calculating with probability. So I am excited, because next week we are literally going to be taking everything that we've learned from this class so far, and we're going to put it all together and learn the hypothesis testing steps. So let me know if you have any questions, and I hope you have a great day.